Welcome once again to our course. So far we have discussed about the Metallocene based catalysts and very extensive discussion we have done, how it has been developed, how it has been so popular in industries for polyolefin synthesis, and not only for its reactivity, activity, and also for its stereoselectivity for the polymers, where we will be using the prochiral monomers. You can tune the fine properties, you can use as a toolbox, you can also convert it to a heterogeneous catalysts, so that it becomes less cost effective and industrially accepted. And today we will start a new topic, which is metal-carbene based organometallic compounds for similar polymerations. Although compared to the Metallocene based catalyst, this is relatively less developed, but the prospect is huge. Many monomers are polymerized by metal-carbene based organometallic compounds, where the polymerization is not possible or some difficulties with other catalysts. So, we will start today the metal-carbene based organometallic catalyst. We will start first what is this system, what is the uniqueness of this metal-carbene system, and then slowly we will go to the basic structure, electronic properties, then synthesis, then reactivities, and its application in polymerations reactions. So, let us start. So, today, as I told, I will discuss the metal-carbene complexes as a versatile catalysts for multiple useful reactions. This is very important first before going to the polymerization reaction. Okay. So, let us start today. So, we will learn the concept of metal-carbene complexes, metal-carbene complexes as alkene metathesis catalysts, and also we will learn today the types of metathesis reactions. Okay. Here metathesis, not sigma metathesis, here we will alkene metathesis or alkyne metathesis reactions. Okay. So, this you know that this is alkene, all we know, and this is the alkyne. Okay. Everybody knows, and we are very familiar with this one. The alkene, this carbon is sp2 hybridized, and these two carbons are sp hybridized. Okay. And this is, we know that this is a planar, the alkene, and alkyne is a linear structure. If suppose we have the similar compounds, instead of one carbon, if you have like metal carbon bonds, this one, okay, and it obviously there is the ancillary ligands, that is this one. So, it is basically analog, the metal analog of the alkene. If this formal structure is possible, then we call it is metal alkene, metal carbene. Okay. So, this kind of complex is called metal carbene. So, what we are doing basically, if you replace this carbon by a metal center, then it is metal carbene, not metal alkene. Okay, pi complex. Similarly, here if we replace this one with one metal, then you will get this kind of structure. This is similar as metal alkene. This will be metal carbine. Okay. Okay. So, this is, and here obviously the ancillary ligands. So, this will be your metal carbine. So, here you will see there is a formal double bond between carbon and metal. Okay. Here, so there you will see that the formal double bond between the metal and carbon. in this kind of complexes we call metal-carbene complexes. If you have a triple bond, formal triple bond, then it is metal-carbene complexes. Okay, and you will see that how these kind of complexes are interesting not only for its structure, academic perspective, but also its versatile applications in different sectors, like to make the valuable organic synthesis, for the synthesis of valuable organic compounds, for especially in medicinal drug industries, and also for the polymer synthesis. Okay, and you will be surprised that this type of single complexes can do several type of metathesis reactions. Okay, now what is metal-carbene? We will just try to discuss in little bit depth before going to the to understand what is the metathesis reactions. Okay, so as I told already that this is in the metal-carbene complexes, you will have a formal double bond metal-carbene. So you can I am just writing as a third bracket, that means there is other ancillary ligands are there. Okay, it just in a simplified form, and if you see the canonical form, you might have this one minus C plus, or you might have this form. So here you will see one metal, in one case, the left side case, the metal center is electrophilic, and the right side it is nucleophilic. Okay, so here depending upon the canonical form, it can behave in different way, either it is as a electrophilic or as a nucleophilic. I am telling about the properties, electronic properties of the metal centers, and oppositely just reverse scenario will be on the corresponding attached carbon centers. Okay, now all we know that this is the which group? This is methylene group, and this is highly reactive methylene group. Okay, if you recall our 10+2 chemistry or BSc first year chemistry, we have read about the carbene, organic carbene, carbon based carbene chemistry, like Reimer-Tyrmer reactions like that. So you know that this methylene can exist in two spin isomers, and these are very reactive. Okay, and what are the isomers? So this we can draw it. So this is, let us say I am writing in a general form. So like R may be hydrogen or other alkyl group, and okay, so you know that this is the sp2. So this one and this one is basically sp2 hybrid orbitals, and this is actually pz orbitals. Okay, and now if there is a possibility of two spin isomers, one is, let us say, the two unpaired electrons. Okay, you know that valency of the carbons is 4. So two unpaired electrons may be paired up, act as a lone pair housed in sp2 hybridized or hybridized orbitals. In other case, what may happen? In other case, so this is similarly, okay, and this is your sp2, and again this is pz, and this is your sp2. So what will happen now here? Another possibility that one electron is here and one electron is here. So you will see that this is, if you calculate the multiplicity, it will be 2 into 0 plus 1, that means 1. So it is singlet, okay, and this one half and half, so 2 into 1 plus 1, so it is 3, that means it is triplet. So that is why these are basically the spin isomers, okay. And you know that these are very reactive like methylene, okay, or Cr2 dot, very reactive. It's actually behave as a transient species in various reaction. That means it's very difficult to isolate, okay, but it may behave as a intermediate or transition state. And instability by both the kinetic and thermodynamic issues, and that is why it actually forms a strong metal carbene bond. So when there is a possibility like a metal species, transition metal species, and you have this carbene, so it forms like that, okay, and this is basically, so we can tell that forms strong metal carbene bond by disfavoring carbene dissociation. So it's basically the free, this is called free carbene. This free carbene is very unstable. So this free carbene is now, after reacting with metal, suitable metal species, it may be neutral, cationic, okay, maybe transition metal, maybe non-transition metal, it can react to form the metal carbon bond and stabilized, okay. So you understand that in later we will understand that how what type of bond exists between the metal and the carbene, and what are the orbitals are involved, okay. So that we will discuss in later in detail. Today we will just try to understand that what are the reactions, okay, and what are the applications of these metal carbene catalysts. It's basically so that we be excited and inspired to study. So this is, you see in this screen, you see this is a alkene metathesis reaction, a simple example of alkene metathesis reactions. If you see very carefully what is happening here, okay, here you will see that this one and this one is same group in one alkene, R1 R1, and here is another group, let us say R2. Now if we put the catalyst like any carbene catalyst, what will happen? You will see that the reactions here R1, both the cases in both the alkenes, R1, R1, R1. Here you will see I am just crossing R2, and here you will see all are R2, R2, R2. That means, if you see, okay, very roughly what is happening here is basically here it is clipped. So, you are forming formally, okay, then we will discuss the mechanism later, do not worry. So, this one like this formed like this one, and now it is again, so cleaving the carbon carbon double bond and then again threading. So, cleaving and then threading. Okay. So, this thread now may happen like a two ways. One is this self, okay, and this two species of this. So, this self coupling, this self coupling will form this one, and the other self coupling will form this one. Although there is a chance of forming the again the starting material also. Okay. So, there is also other possibility of the original alkene. So, this will be in equilibrium. So, you understand this catalyst. So, is basically breaking a very stable alkene bond and then again threading, and what we are getting? We are getting basically two new alkenes, and this is the applications. So, you can make new alkenes from one alkene by a metal-carbene catalyst using the alkene metathesis reactions. Looks very simple. What we will do from the new alkene? This can be done in other ways, but there is a lot of applications. Okay. I will discuss so that you will be understanding. This one is we already discussed in the last classes. It's just a recall that how important it is the olefin metathesis reactions and developing the catalysts. So, this is a SWAP process. SWAP means we already discussed is a cell higher olefin process, okay, SHOP. This for many purposes these SWAP reactions have become famous, not only to make a valuable organic compounds from a smaller alkene, but also to make a new or higher alpha olefins for copolymerization, alkene copolymerization to make LLDP. So, we have discussed how important it is. So, if you recall this step from here, okay, to this one, if you recall, we used a olefin metathesis catalyst. So, this is basically the olefin metathesis reactions, and what catalyst we use? If you remember, we use the one oxide, that is the molybdenum oxide. That is the second step of the SWAP process, SHOP process. So, here what you will see that in this case you can make a different type of higher alkenes, okay, higher alkenes by the olefin metathesis reaction. The mechanism will come in detail, but I just try to give some highlight about its use applications. So, here we already see that used the alkene metathesis reactions. Okay. In the following lectures, we will discuss in more depth about the catalyst design and the mechanism. Okay. So, here you see same thing happen here. So, if you have a like different type of alkene, we will understand what kind of reaction it is. It is called the cross metathesis reaction. So, it is basically you see this R1 R2, R3, R4 groups. These are basically scrambling, okay, scrambling around the alkene bond, double bond, okay, fine. So these are the milestone of the metathesis developing metathesis catalyst, okay. You will see that around 1950 different oxides type or carbonyl type, firstly oxides type catalysts are developed for different purposes. As example, you see already you know that molybdenum oxide was used for soft process. Then different carbonyl compounds are developed or discovered for metathesis catalysts, and then slowly stock graphs came in the picture, and now in around 2000 you know that this metathesis catalyst has been enriched by the huge contribution of graphs, and today you know that in a multi-step reactions like 20 or 15 steps in drug, medicinal or drugs industry, you cannot really think any scheme without the alkene metathesis using the graphs catalyst reaction. It's so useful, okay. And although there are other catalysts like stock based catalysts, Hoveda type based catalyst, okay, there are a lot of metal-carbene catalysts have been developed time to time. We will discuss in more detail about what are the metal centers, what are the ligands, how does it work. So this is again that we let's see try to understand that what is the metathesis reactions. So this is basically the reactions around the carbon-carbon double bond, okay. You will see that there will be change of the substituents, change of the carbon atoms, okay, and change of the structures around the metal center. You will understand when I will discuss the types of different alkene metathesis reactions. So for as told that we should not we cannot really discuss any metathesis reactions without remembering these trios, that is the Robert Grubbs, Richard Schoch and Chauvin, because they are the pioneers, they are the discoverer, and due to them, due to discovery of this type of catalyst, many problems in organic synthesis mainly have been sorted out and the process has become more easier, and also definitely this opens up a new catalyst for a different type of polymerization, alkene polymerization of different type of complicated monomers, okay. So and that's why for their great contribution they were awarded Nobel Prize in 2005. So you will see that this chemistry is not really very old, okay, it's relatively new, okay. So these are the some important metathesis catalysts. So this you see that this is Fischer-Carbene catalyst, Fischer-Carbene complexes. These mainly you will see that metal center is low oxidation state, okay, low oxidation state. We will discuss in more detail what is Fischer-Carbene, what is Schoch-Carbene complexes. This I just want to give a highlight about different or to introduce the structure of the metal-carbene complexes. So this is, you will see this is one example of Schoch-Carbene complexes. Here the metal center will be relatively higher oxidation state, okay. Now this is, you will see this is also another metal-carbene, this is vinylidene complexes, okay. Here you will see because this the structure due to this one, this called the vinylidene complex, okay. And this is a hybrid of Fischer and Schoch complex. So you will see the how there are many possibilities of versatility in the metal-carbene complexes, and more opportunity or more versatile means more easy way to tune the electronic properties and to tune their reactivities. This is N heterocyclic carbene complexes, as we told that free carbene, okay, free carbene are very unstable, okay, is unstable, okay. The N heterocyclic carbene, especially developed by Ardingo, they showed that some of the organic carbenes can also be stabilized if we design the carbene judiciously, okay. So here you will see that in this is called NHC, N heterocyclic carbene, and here there will be statically demanding groups on the nitrogen, so that the carbene is stable, okay. Some of the carbenes, free carbenes, can also be isolated. So that is really amazing. That was one of the problem in this carbene ligand synthesis, because you have to be really very careful and you need a expert hands to make the carbene ligands, okay. So here some of the real metathesis catalysts, okay. In the earlier slide we discussed the structure of the metal-carbene complexes, and here some of the very famous metal-carbene metathesis catalyst, okay. I am sure you have heard the Grubbs catalyst, okay. I am very much sure, okay. And you know that what metal is in the metal center in the Grubbs catalyst? Any idea? Yes, it is ruthenium, okay. And what is the oxidation state? This is +2, okay. So we will discuss in the next class about the nature of the ligands of carbene. How does it is actually regarded as a phosphines, okay, and we will discuss why. And it is neutral. So metal-carbene ligands is a neutral ligand. So when you calculate the total valence electrons to check that whether this molecule is satisfying 80 electron rule or not, you have to count 0 for the carbene, and it is regarded as phosphine, okay, ligand. So that's why the metal-carbene, the carbene ligands is very good substitute of the phosphine ligands, because some of the phosphines are toxic, not very healthy. So here you will see this is called the Grubbs first generation catalyst. In some book it is just simply written as G1, okay. Then second one is, you will see this is the Grubbs second generation catalyst. Here you will see this is the cyclohexyl phosphine, tris cyclohexyl phosphine. This is the PCY3. This PCY3 has been replaced by NHC, okay. One of the PCY3 has been replaced by NHC and other moieties are same. So this is Grubbs second generation catalyst, okay. And this one is called Hobeda-Grubbs catalyst, HJ catalyst. So this is also here you see that the second PY3 has been replaced, and this phenyl group has been functionalized by a isopropoxide, and that oxygen actually weakly donates to the ruthenium center, and this is very reactive, quite reactive. On the other hand, stock is mainly for molybdenum catalyst. Here you will see this is high oxidation state, as I told, this molybdenum, and this also used for different reactions and heavily used in alkene polymerization. So stock catalyst, the main difference is the high oxidation state metal center, and the Grubbs catalyst is a kind of Fischer type of catalyst. These are low oxidation state metal centers, okay. So these are the very recent, okay, I mean we can say comparatively much newer chemistry, and these are highly efficient olefin metathesis catalysts. You will see that most of this chemistry was developed in around 90 after 90. Okay, so this from 1990 to 2005 was the actually golden era for developing metathesis catalysts. All of the catalysts actually have been developed in that area. So these are also very similar. So this you will see that this has been used as a axial the chirality has been induced by using the concept of axial chirality. And other thing is very much similar. You see this one and this one is very much similar. Okay, the Grab's third generation catalyst, here you will see that instead of one here instead of cyclohexyl phosphine. So initially, if you remember, this one was there. This has been replaced by one pyridine, 3-bromopyridine. Okay. Then the Grela's catalyst, that is also very much similar as the Hoveda Grab's catalyst, and the Pierce catalyst, you will see that this is also N heterocyclic carbene type catalyst. So all are very much similar, just the ancillary ligands or the ligand surroundings have been changed. Okay, and you will see that main structure, okay, the main unit is actually this one, this the metal-carbene part. Okay, and you see that how with tiny change of the ligand environment can enhance the reactivity by influencing the electronic properties. So that is really amazing. Okay, so in the next class we will be continuing about the different classes of metathesis reactions. You will see that using the same catalysts, metal-carbene catalysts, we can do various type of metathesis reactions. We can increase the number of the carbon atoms of alkene. We can make the cyclic alkenes or alkyne. If I use the alkyne precursor substrates, we can make the polymers by using the appropriate alkene monomer. We can also do the ring closing metathesis reactions. That means to make a very big cyclic alkene, very big cyclic carbon derivatives, and also we can do the cross metathesis reaction. That means we can make a new alkenes from a particular alkene by using this kind of metal-carbene catalyst. And these reactions are very efficient, not only to make the valuable organic compounds, but also for the polymer industry. So next classes we will discuss about the electronic properties and the orbital overlap between the metals and the carbene species, and also we will try to see that what the nature of these carbene ligands. Okay. So thank you and see you in the next class.